Okay, so I'm going to talk a little bit about the second derivative. Okay. Now the methods for the second derivative are exactly the same as the first derivative. So if you ask to find the second derivative of something, it just means that you're differentiating twice. Okay. So for example, if you had started with a cubic, the second derivative will give you a linear function because you go cubic to quadratic and then quadratic to linear. Okay. More importantly, the reason that we look at the second derivative is to understand things from a geometrical perspective. We know that the first derivative gives us information about the gradient of our original function. Okay, so meaning it's like it describes the rate of change. So that's where this diagram is useful. Okay, you've got three graphs here. The top one is what we might consider the original function, okay, which, okay, given its shape, could be a quartic, okay, most likely is, I think, which is why you've got those two humps there. The graph below that is the derivative, and so we have it represents the gradient of that first original function. So we've got a cubic, and then below that is the second derivative, which is a quadratic. Okay, so the second derivative describes the rate of change of the first derivative. Okay, so if we just compare the first derivative with the original function, we've already seen how our okay, just need to fix something up in here. It's not working properly. Okay. Okay, so we can see at this point here we have a local maximum turning point. And so we know that the value of the gradient, and hence the derivative at our stationary point here, is 0, because if we were to draw a tangent, then we have a horizontal line. And so that corresponds to this point down here on our first derivative, where it's equal to 0. Okay, so those dotted vertical lines kind of just show the relationship between the 3 points: your original function, your first derivative, and your second derivative. So where we have that local maximum on our original function, that corresponds to a value of 0 for our first derivative. And it also, if we go down further, we can see that that will correspond to a negative value on our second derivative, because it's below the x-axis. We can also see that to the left of our stationary point on the original function, we have a positive gradient. Okay, so all of this area, all of this area here, okay, the gradient is positive. Okay, to the left of point Q, which is why when we look at the derivative function, it's above the x-axis, okay, indicating the sign here. This is all positive, okay, which relates to a positive gradient on our original function. We can see that the slope of our original function is quite steep to start with, but it gets flatter and flatter as it gets closer and closer to a value of 0 at the stationary point. And we can see that happening here on our derivative function. It starts up here like a relatively high value for our derivative, but that value is getting less and less as it approaches 0. Okay, and then as we go past point Q, we can see now our derivative is negative, corresponding to a negative slope on our original function. Now, how does that relate to our second derivative? All of those values here are negative on our second derivative. It only stops being negative at this point. What is that point? R. R1 and R2 relating to this point R on our original function. This point here is our point of inflection. Okay, it's not a stationary point of inflection, it's just a point of inflection. What do I mean by a point of inflection? It is the point at which the concavity changes. Okay, so I'll just erase some of these things here. Okay. Okay, so this part of the curve that we can see here is what we would call concave down. Okay, we have that hill, but if we think of it the other way around, it's got that concavity where it's actually concave down, relating to a maximum turning point. Okay, to the right of this value R, it is the concavity has changed to now concave up. Okay, so that point of inflection changes the concavity from concave down to concave up, or vice versa. Okay, another point on there which would be a point of inflection would be here at point T. Okay, it's changing from concave up to concave down. Okay, so that's what those points R and T are. And on our second derivative, those points of inflection relate to a value of 0 for our second derivative. So our second derivative is 0 when we have a point of inflection. Okay, now that information really is math specialised information, but I just thought may as well talk about that now, just so that we get an idea and familiarisation with how it all relates together. The most significant part that we're interested in, as far as the course we're working with and our second derivative, is the sign. Is it if it's positive or negative for our second derivative? So whilst we've seen that we can work out whether a turning point is a maximum or a minimum by using our gradient table, we can also see whether a turning point is a maximum or a minimum by substituting the value at our stationary point into our second derivative. So we can, if we look at that, we can see our maximum turning point at Q relates to a negative value for our second derivative. If we have a look at our other maximum turning point at U, track down and look at our second derivative, it's negative there as well. Our minimum turning point here at S, that should be an S, okay, that corresponds to a positive value on our second derivative. So there's a couple of ways that we can work out if a turning point is a maximum turning point or a minimum turning point. We can use our gradient table, or we can find our second derivative and just substitute the point into our second derivative. And if it's positive, it's a minimum turning point. If it's negative, it's a maximum turning point. Okay, it might be worthwhile sort of noting that on somewhere. Maximum turning point corresponds to a negative value for second derivative, which is labelled as f double dash x, okay, but also written as d2y dx squared. There's a couple of different notations, okay, for your second derivative. F double dash x or dy dx, but with the d squared and the x squared, kind of strange notation, but that's it. A minimum turning point corresponds to a positive value for f double dash x. Okay, our second derivative. Okay, so I guess another way to put things is that our first derivative describes the rate of change of our original function. Okay. The second derivative describes the rate of change of the first derivative. So if we just compare our second derivative with first derivative with the second derivative, we can see that our minimum turning point here corresponds to a zero value for a second derivative. Okay, and also that maximum turning point at t1 on our first derivative corresponds to a zero value of our second derivative. So it's the same. We just got to think second derivative is describing the gradient of the first derivative, just like the first derivative describes the gradient of our original function. Okay. So we don't really need to spend a lot of time on that, but there may be an odd question or two where we just need to keep that in mind.